Hello, everyone. Welcome to George Mason University's Observatory. It's 8 p.m. Eastern, December 3rd, 2020. We hope you are all safe, healthy, and doing well. I'd like to welcome you to our final public virtual evening under the stars for the semester. To find out more information, if you haven't visited our observatory before, you can read more about our facility at science.gmu.edu/observatory or follow us on Twitter at GMU Observatory. So tonight, unfortunately, the weather is cloudy, so we will be having a closed dome tour with our observatory. Tonight's a Thursday night, and in the fall semester, we've had our events on Thursday nights, but next semester, starting in February, these events will be held on alternating Wednesday evenings. We look forward to having you join us in February for some clear winter night viewing. Sorry, my slides just skipped ahead. So here's some pictures of our observatory being used and our public lectures. We look forward to welcoming you back in person sometime, most likely in the 2021-2022 academic year. We're currently planned to be all virtual for the spring semester. We're located atop Research Hall on the Fairfax campus, the main campus of George Mason University. And here's a picture in the middle of our control room located on the roof next to the dome, one of the iconic structures on our campus, surrounded by a collage of some of the photos that have been taken with our 0.8 meter diameter telescope. All right, so I'm getting some messages that people can't hear me. Can I get, William, can you do an audio check? Can you hear me okay?
I can hear you okay.
Okay, so the person messaging me, it might be an audio connection.
Wait, which William?
The William Masco, we're good, thank you. Okay, so to follow the current events that we have, we publish a monthly newsletter, The Moon. The December newsletter will be coming out next week, and you can sign up for the newsletter at our website. We also have a philanthropic organization called the Patrons of the Observatory to continue to produce our events and outreach that we do for the Washington, D.C. community. We could use your help, and so your tax-deductible donations provide critical support. And we would like to thank our Big Bang Galaxy Supernova and New Nova Cluster and Star members. You can join today. Once again, for more information, you can go to science.gmu.edu/observatory. I'm the director, Professor Peter Plavchan. We have with us tonight Professor Rob Parks, the deputy director of the observatory. William Matsko and Justin Wittrock are the observatory graduate teaching assistants. And if you're a student here at George Mason, on Mason 360, you can find our student club, Friends of the Observatory. And our president this year is Brandon Iverson. We also have student tour guides that give tours, and a student is asking for some information about some credit for tonight, and I'll respond to the messages soon. If you have any questions tonight at all, please use the chat, and either one of our tour guides tonight who are here with us, including Andrew and Owen, we will answer the questions in the chat. Here's a picture of our telescope, and you can see for scale, there's a computer in the background. I'd also like to bring to your attention, if you're a student here at Mason, a new general education course available, Astronomy 303 on black holes, that will focus on the qualitative understanding of black hole systems to give you a necessary background to appreciate the differences between Newton's theory of gravity and Einstein's theory of relativity that predicts the existence of black holes, and that'll be offered this spring of 2021. It is my pleasure to introduce to you tonight's speaker, Dr. Sarah Horst, a professor at Johns Hopkins University. She earned her undergraduate degree at Caltech and her PhD at the University of Arizona. She will be, and then she was a National Science Foundation Prize Postdoctoral Fellow at the University of Colorado. She's going to talk to us before coming to Johns Hopkins. She's going to talk to us tonight about her research on Titan and hopefully maybe tell us a little bit about the Dragonfly mission. So Dr. Horst, the floor is yours.
Awesome. Thank you so much. Can everyone hear me okay? Or at least some people hear me okay? Okay, I see a thumbs up. Awesome. Okay, let's see if I can pull off the screen sharing. So far, so good. And you can see my slides? Awesome. Okay. Thank you so much for having me. I know this isn't the way that any of us would want to be doing this, but it's still great to share some exciting science with everyone tonight. So tonight I'm going to be talking about Titan, which is the largest moon of Saturn. And the story that I want to tell you is just kind of the story of being a planetary scientist. And I think one of the main jobs that we have as planetary scientists is taking points of light in the sky and turning them into worlds that we can understand and study and think about in the same way that we think about our own Earth. So this is Saturn. Not Titan, although you can see Titan in this image, and I'm realizing without a laser pointer, it's a little bit harder to show some things. But Titan is the, kind of little fuzzy orange ball that's off down to the bottom right of your screen. And this is just to give you a sense of scale. This is a beautiful image from the Cassini mission. And that, oh, now my slides won't advance. This is where we end up, but where we start is with Galileo. So Galileo discovered Titan, and the picture that you're seeing, or sorry, Cassini-Huygens discovered Titan, and the picture that you're seeing is the discovery data. So we didn't have beautiful cameras attached to telescopes back then that were taking pictures, and everything was drawn by hand. And using the state-of-the-art at the time telescope that Cassini-Huygens had built, this is what Saturn looked like to him, kind of a circle with ears, which turned out to be the rings. And the little asterisk that you see in this picture, which he was tracking the position of over time, turned out to be Titan. And so he discovered by watching over many nights that this object was very clearly orbiting Saturn and turned out to be this large moon. It was a long time before we could learn anything else. Telescopes just weren't advancing enough to really tell us more than there was this moon orbiting Saturn. And so it was the early 1900s when we kind of got our next piece of interesting information. And again, this is an image that was drawn by hand, not taken with a camera. And what you see here is the first suggestion that Titan had an atmosphere. And so what you were seeing is basically potential evidence that there is some kind of way that light is interacting with Titan that would indicate that there's gases around it. But again, it wasn't really clear that that was true. And it was going to take us many more years to be able to learn anything else. So the process at the beginning of turning this point of light into a world was very, very slow. It was another 40 years about before we got conclusive evidence that Titan did have an atmosphere. And that came in the form of this amazing piece of information, which is called a spectrum. And so here what we're looking at, and this is a tool that we often use, is the way that light interacts with an atmosphere. And each molecule that you might see in an atmosphere imparts something that's very similar to a fingerprint on that light. We call that a spectrum. And this is the spectrum of methane. So Gerard Kuiper was using his telescope to look at Jupiter, Saturn, Jupiter's 4 large moons, which we call the Galilean satellites, Europa, Io, Callisto, and Ganymede, and Titan. And when he looked at Saturn, Jupiter, and Titan, he saw this fingerprint, but not when he looked at the Galilean satellites. This fingerprint is the molecule methane, CH4. And this was the discovery that indeed Titan does have an atmosphere. And also the realization that Titan is very different than those 4 large satellites of Jupiter, because we now know that in fact, Titan is the only moon in the solar system that has an atmosphere. And so I've always felt that the title of this paper by Gerard Kuiper, which was Titan, a satellite with an atmosphere, should have had like a question mark or an exclamation point or something like that at the end of the title, because this was a very surprising discovery. And as we moved forward in solar system exploration, it really turned out to be that Titan is this very unique object. So just to give you a sense of what this would really look like, this is a great graphic that was put together by Emily Lokdawalla at the Planetary Society. If you don't know the Planetary Society already, you definitely should if you're interested in space science. But these are what Emily calls the not planets. So these are round or round-ish worlds in our solar system that are not planets. You'll hopefully recognize that some of them, at least, Earth's moon is on here. We have those 4 large satellites of Jupiter, Io, Europa, Ganymede, and Callisto. Pluto and Charon are on here. Triton, the satellite of Neptune, is here. Titan's front and center in the middle. And when you look at this graphic, again, it really brings home this idea. All of these other worlds, you can see their surfaces, you see their impact craters, you see the evidence of volcanism on Io, you see all of the interesting tectonic features on Europa. But when you look at Titan, you don't see the surface. And that's because its atmosphere is in the way. And so again, this is a weird thing in our solar system. So after Kuiper, not a lot happened, which is kind of a theme in this story of planetary exploration with fits and starts. It took many, 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 many years before we could really do much more using telescopes on Earth. But in that intervening period of time, we started sending space robots to explore the solar system. And this image was taken by the Voyager spacecraft as it flew through the Saturn system. I always like to joke with people that you too can recreate the Voyager flyby of the Saturn system at home with an iPhone and an orange. You'll find out about as much science as we found out from this image, although your image will be slightly higher resolution than this one. So this was really frustrating as a planetary scientist, right? We were working to turn points of light into worlds, and we turned this point of light into a fuzzy orange ball without any information about what was going on the surface. There could have been 20-foot tall aliens waving at the Voyager spacecraft as it flew through the Saturn system, and we wouldn't have known. So this is frustrating as a planetary scientist. Voyager was carrying other instruments though, and one of those instruments was called IRIS. It's an infrared spectrometer, and so it's looking at light from the sun in the infrared. That light interacts with Titan's atmosphere. And again, we have the fingerprints of all of those different molecules that get imprinted on the light. And so that's how we're trying to figure out what Titan's atmosphere is made out of. So from Kuiper, we knew there was methane. From Voyager, we find out that there are a bunch of what we call organic molecules. And here I don't mean that it's like free range, non-GMO, very expensive at Whole Foods or whatever. I just mean that it's a molecule that contains carbon. And so from Voyager, we found out that Titan's atmosphere has things like propane if you want to barbecue with your friends and family socially distanced this weekend. There's hydrogen cyanide if you don't like your friends and family very much. So there turned out to be this whole host of organic molecules in Titan's atmosphere, indeed molecules that we had never seen in other atmospheres. And so these two pieces of information combined were really frustrating. We knew that Titan had this rich organic chemistry in its atmosphere. That might mean that there's the possibility of life on Titan, and yet we couldn't see down to the surface. And so we left the Voyager encounters of Titan and through the Saturn system with so many more questions than we started with, which is a theme in planetary exploration. And so we really wanted to immediately go right back to Titan. Let's go, let's get going. But NASA has a different definition of immediately than the rest of us. And so it was a number of years before we were able to go back. I'm going to talk a little bit about some of the things that we did learn from the Voyager flybys before I talk about the next steps in exploring Titan. So Titan is really unique in the solar system. I think I've emphasized that point before about the fact that it's the only moon with a significant atmosphere. It's the largest moon of Saturn, and indeed it's the second largest moon in our solar system. Ganymede is just a little bit bigger. It has a mass of about 0.0225 Earth masses, which gives it a density of about 1.9 grams per centimeter cubed. That means it's about half rock, half water ice. And we now know from the Cassini mission that it's at least partially differentiated, which means like the Earth, the heavy stuff has kind of sunk into a core. And so that means that the rock is in the middle and all of the ice is on the outside. The surface temperature is 94 Kelvin, which is about negative 290 degrees Fahrenheit. That's so cold that I don't even, it loses meaning for humans because we really just don't have any context. But at that temperature, water ice behaves like granite. And so that's something to keep in mind as we're exploring Titan further. The surface pressure is about 1.5 bar. So that's 1.5 times the surface pressure at sea level. But with that colder atmospheric temperature, that means that Titan's atmosphere is about 4 times as dense as Earth's atmosphere at sea level. So one of the things that's important about that temperature and pressure, and I apologize, there will be a couple of graphs in here that you have to look at. This is what's called a phase diagram. And so on the bottom, we're looking at temperature, and along the side, we're looking at pressure. And these are the different phases, solid, liquid, and gas, of methane. So this molecule that Gerard Kuiper had found. And at Titan's surface temperature and pressure, which are labeled with the red T on this graph, we are very close to what's called the triple point of a molecule, the triple point of methane. So at the triple point of methane, methane can exist as a solid, liquid, or gas, depending on just shifting the conditions a little bit. And this is very similar to Earth, right? Here on Earth, we are very, very close to the triple point of water. That's one of the reasons that we have this amazing hydrologic cycle. We have rain, we have snow, we have, all of these different weather events. Here in Maryland and Virginia, I think we sometimes have all of those things at the same time, which was not something I understood before I moved here. But this is one of the things that makes Titan so interesting. Right off the bat, only knowing the temperature and pressure at the surface, we can already tell that really interesting things are going to happen here because we're close to the triple point of methane. So I mentioned that Titan has this dense atmosphere. Titan's atmosphere is actually mostly molecular nitrogen, which I haven't mentioned yet. The reason that I haven't mentioned it yet is that nitrogen is a really boring molecule when it comes to the fingerprint that it imprints on light. And so it's actually very hard to detect in an atmosphere. And so even though we were able to detect the methane in 1944, it wasn't actually until the Voyager encounters that we were able to really definitively prove that the other main molecule in Titan's atmosphere, 98% is molecular nitrogen. So one of the reasons that's so interesting to us is that the only other atmosphere in our solar system that has nitrogen as its main component is Earth. So Earth and Titan both have molecular nitrogen dominated atmospheres. We don't tend to think of Earth that way because we are very concerned with being able to breathe, which is important. And so we tend to think of Earth as having this oxygen atmosphere. But in fact, the main component is still nitrogen. And we think that before the origin of life on Earth, which is the reason why we have oxygen in the atmosphere, that Titan's atmosphere and Earth's atmosphere were actually really similar in terms of their composition. And so that's one of the reasons why we're so interested in understanding the processes that are happening in Titan's atmosphere today. I always like to tell people that we can't, or at least we haven't figured out how yet, to build a time machine and go back to the time in Earth's history when life originated, but we can and do build spacecraft and send them out into the solar system. And so we can use Titan to study those processes that were happening in Earth's past. So in addition to those molecules, we end up with all kinds of other things, and I mentioned some of them before. So when sunlight hits the methane and nitrogen in Titan's atmosphere, it initiates something that we call photochemistry. So the light, because of the energy that it carries, can break up a bunch of the molecules in Titan's atmosphere. And when it does that, they become very reactive. They're all running around trying to find a new friend to make. And when they make those friends, they often make new molecules. And so we end up with a whole bunch of molecules that we call hydrocarbons, which are molecules that are just made of carbon and hydrogen, and nitriles, which are molecules that have carbon, nitrogen, and hydrogen. And so we have all of these different new molecules running around, the propane that I mentioned, the hydrogen cyanide that I mentioned, all kinds of different molecules. And subsequent chemistry between those molecules actually converts the gases into solid particles. And so we end up with what we call haze in Titan's atmosphere, which is really highlighted by this image. So it's not an artifact of your computer or image processing or anything. This blue ring around Titan are haze particles in its atmosphere. These processes are very similar to the way that smog is formed here on Earth. And then finally, one of the other things that turns out to be really interesting about Titan's atmosphere is that there are some oxygen-containing molecules. The most abundant one is carbon monoxide, which has an abundance of 50 parts per million. That doesn't sound like much, but that actually makes it the fourth most abundant molecule in Titan's atmosphere. And the reason that we care about oxygen goes back to these questions that we have about the origin of life on Earth and the possibility of life on Titan. So all of the molecules, all of life on Earth is based on the same small set of molecules, things like amino acids, which are the building blocks of proteins, nucleobases, which are the building blocks of DNA. And all of those small set of molecules are based on the same small set of atoms. And the smallest set of atoms we tend to talk about as being necessary for life as we know it are carbon, hydrogen, nitrogen, and oxygen. And so if you've been paying attention, you already know all four of those atoms exist in Titan's atmosphere, and they're participating in this really active organic chemistry that is happening in Titan's atmosphere. And so just from measuring the atmospheric composition, we're already really excited about the possibilities for trying to understand life. So this is just to give you a quick little schematic of how we have explored the Saturn system. I was mentioning this idea that we turn points of light into these worlds. And we've actually been to Titan a number of times. Not all of them are listed on here, but what you'll see listed on here are the Voyager encounters, and then the Cassini-Huygens mission, which I'm going to talk about in a second. But one thing to notice here is that one Titan year is about 30 Earth years, 29.5 Earth years. So the seasons are much longer. And so one of the challenges that we have in studying Titan is that we really need to be there for a long period of time to see the seasonal changes. And Titan does have very strong seasonal changes. Its axial tilt is 26 degrees, which is very, very similar to Earth's axial tilt. And so Titan has a spring, summer, winter, fall, just like we do here on Earth. Those seasons just last much longer. So I imagine at this point that like fall on Titan probably feels a lot like 2020 at this point. So now I want to talk about the Cassini-Huygens mission, because most of what I'm going to talk about for the rest of this presentation are things that we found out from the Cassini-Huygens mission, which was really transformational in terms of turning Titan into this world that we can really understand. So the Cassini-Huygens mission was a joint mission between NASA and ESA, which is the European Space Agency. It was launched in 1997. It was 7 years in cruise, so it arrived at the Saturn system in 2004. Remember that the Voyager encounters in the Saturn system were in the early 1980s. So when I told you that we were really excited that we had to go back to Titan right away, it took us about 25 years to get back to Titan. So patience is definitely a virtue in studying the outer solar system. What you're seeing in this picture on the right-hand side is the kind of final steps of spacecraft assembly for Cassini before it launched. The Cassini is the orbiter. Huygens was a probe which descended through Titan's atmosphere in 2005. And the Huygens probe is that kind of circular gold disc that you can see. That's the heat shield for the probe. And one thing I always like to emphasize when I show people this picture is that the little white things on the bottom of the picture are humans in what we call bunny suits that keep them clean while they're assembling the spacecraft. So Cassini is not a cute little Mars rover. Cassini was about the size of a school bus. And like I said, the Huygens probe landed January 14th, 2005. Cassini carried 12 instruments and Huygens carried 6. In both cases, these were a mixture of what we call in situ and remote sensing instruments. So the in situ instruments are things that, directly sample materials. So it's the senses that you would think of as kind of like smell and taste and touch. And the remote sensing instruments are the sense that you would think of as listening or as sight. And so some of them require actually ingesting sample, others are done from far away. This gives us a really good ability to characterize all of the different processes that are happening in the whole Saturn system. And Cassini's end of mission was September 15th in 2017 at 7:55 a.m. Eastern. Cassini was intentionally crashed into Saturn as the end of mission. There were 2 reasons for that. The first one is because Saturn is super interesting, and there were scientific questions that could be answered by crashing Cassini into Saturn. Cassini was able to directly sample Saturn's atmosphere and analyze the composition, was able to do really good magnetometer measurements, all of those things. But the other reason is that we have moons in the Saturn system, Titan is one, Enceladus is another, that we think could possibly harbor life. And at the very least, where Earth life could possibly make a home if it had hitched a ride on the spacecraft. So we had to make sure that there was no possibility that Cassini would eventually crash into one of Saturn's moons. And the easiest way to do that, unfortunately, was to incinerate Cassini in Saturn's atmosphere. And so that was the decision that was made. This is what I like to call Titan's baby picture. So this is one of the, actually the first image that Cassini took of Titan. And I think it's such a funny picture because you can see all like the wavy lines and stuff. And nobody's ever even bothered to process this image because they knew that so much better imaging data was going to be coming pretty soon. This was actually even before Cassini went into orbit around Saturn, which happened in July of that year. This is a picture that was taken in March 21st of 2017. And this just goes to show, I think you can see how much variety of different things we see on the surface, which I'm going to go to in a minute. And then let's see. This is one of the last, possibly the last, it's a little hard to tell the way the timestamps are posted. Last image that Cassini took of Titan on September 13th. So if you were paying attention to those dates, this was very, very close to the end of mission. In fact, Titan was used because of its gravity to put Cassini on its crash course with Saturn. So we were able to get a few last images before the mission ended. So I'm going to take a couple of minutes to walk you through some of the kind of major discoveries that Cassini made, Cassini and Huygens made about Titan, and try to put them in context a little bit about what that means for chemistry and for our ideas about searching for life on Titan, and also understanding the origin of life on Earth. So we built a new fancy spacecraft, which cost a fair amount of money, and it had a much higher resolution camera than we had on Voyager. So we get our fuzzy orange ball, but now in higher resolution. But we were able to learn a lot more things. So one of the first things that we were able to study are the haze layers, which I had mentioned before, this kind of smog that encircles Titan. We were able to see that there's a lot of structure, which tells us about how the air moves in Titan's atmosphere. And from some of this data, we were also able to think about things like what these particles are made out of. We think that those particles are made out of basically like any kind of organic chemistry word you could think of. So those hydrocarbons and nitriles that I mentioned before, amines are molecules that contain nitrogen and hydrogen. Aromatics are things like benzene, for example. So basically all of the organic chemistry you can think of is happening in Titan's atmosphere and is contained in those haze particles. One of the other things that was so exciting that we were able to study in more detail from Cassini, although they were actually discovered from the ground in the mid-90s, are clouds. So I mentioned that Titan is very close to the triple point of methane, and that means that methane is able to cycle back and forth between the surface and the atmosphere, just like water does here on Earth. And so one of the consequences of that is that we have clouds on Titan, we have rain. Those clouds are made mostly of methane, but also a molecule called ethane, which is C2H6. That's the primary product when we have the sunlight interacting with methane and breaking those bonds. The main carbon-containing molecule that gets made from those processes is ethane. And so we have methane and ethane clouds and rain. It turns out that Titan probably has at least like 5 or 6 other flavors of clouds made out of different organic molecules that are made in the atmosphere. Things like benzene. It turns out that there's a giant hydrogen cyanide ice cloud at Titan's South Pole. So it's definitely like a nice place to send a space robot, but you probably wouldn't want to visit yourself. One of the things that we were able to benefit from the Voyager spacecraft, which is one of the reasons why we like to follow on exploration after we've gone somewhere for the first time, is that we were able to really specifically design the instrumentation to reveal Titan's surface to us for the first time. And so that's what Titan actually, Titan's surface looks like. Now we're not looking in the kind of like approximation of what our eyes would see, which is that yellow-orange ball that I have been showing before. Instead, we're using a trick where we look in a very, very, very narrow wavelength of light. So just a teeny tiny amount of light. And this particular wavelength sees a good chunk down to the surface, although you can still see it's pretty fuzzy. So it's challenging to image Titan's surface, even if you know what you're doing. We sent the Huygens probe to the surface, which I mentioned before. And this is one of the images that it returned from the surface. If we were all in person, I would ask you to raise your hands and guess what you're seeing here, but we're not, so we're going to skip that part. But what you're seeing here are what are technically cobbles in geology terms. They're about 10 centimeters across. They are made probably out of water ice or a combination of water ice and organics, and they are rounded, which indicates that they have undergone erosional processes on Titan, probably tumbling through flowing fluids. So the interpretation of where we landed the Huygens probe is a dried wash. It's a little bit harder to describe that here on the East Coast than when I was in Tucson, Arizona. But these are regions where most of the year it is very, very dry. It doesn't rain at all. But during certain parts of the year, it rains, and it rains hard, something similar to a monsoon. And so you have these huge flash floods. They transport all of these materials, they roll the cobbles and round them, and that's where we think we landed. Titan's surface is made mostly of water ice, which I mentioned before. We know that because we know from Titan's density and also from some gravity measurements that the rock has gone to the interior, and so it's water ice on the surface. There might also be some ammonia. That's really an outstanding question that we're hoping to answer with Dragonfly, which I'll talk more about at the end. We had other tools to study the surface, though, besides the camera. So the picture I just showed you was from Cassini's cameras. This is not an image in the technical sense. It's not from a camera. This is from Cassini's radar. And so I want to orient you a little bit to what you're seeing when you look at a radar image. So when you look at a radar image, what you're seeing is that anything that is dark is smooth at that wavelength of light. And anything that is bright is rough at that wavelength. So Cassini's radar was 2.2 centimeters. So at 2.2 centimeters, the stuff that's dark in this image is smooth, is absolutely smooth. And the stuff that's brighter is rough. So at 2.2 centimeters, to be smooth, you basically have to be liquid. And so what you're looking at here are giant lakes and seas at Titan's North Pole. We think, for the reasons I mentioned for the clouds and rain, that these lakes and seas are made primarily of methane and ethane. You can see that there's a bunch of streams. This looks very, very Earth-like. If you didn't know better, in fact, you might be inclined to think that this is Earth and not somewhere else in the solar system. And it turns out that there are numerous lakes and seas at Titan's North Pole, which I'll talk about more in a minute. This is a place that we're particularly interested in because all of that chemistry that happens in the atmosphere, those molecules eventually end up on the surface. And in the lakes, there's a possibility of subsequent chemistry because some of those molecules will be soluble in those liquids and some of them will not be soluble. This leads to further separation processes and all kinds of potentially interesting chemistry could be happening in the lakes and seas. So when you look at this image, one thing that you'll probably notice is that there's basically light stuff and dark stuff on the surface, which is about as technical as we can get for our understanding of Titan's surface composition. The dark stuff, if you're looking at the North Pole, are those lakes and seas that I just showed you. The light stuff is our bedrock, which we think is made primarily out of water ice. The dark stuff that you're seeing around the equator in this image, and it reaches from the mid-latitudes in the south to the mid-latitudes in the north, and all the way around the circumference of Titan, are extensive dune fields. So that's a Cassini radar image of one of the dune fields. And one of the things that I hope you are immediately wondering is what the sand is made out of. I told you that the stuff we think of as rock, silicates, is in Titan's interior. It's not on its surface. It's not close to the surface. It's deep down buried. And so what do you make sand out of? And it turns out that we've been able, from a bunch of different Cassini measurements, to learn that these sand-sized particles, which are transported in the same way that sand is transported on Earth, are probably made out of those organics that are made in Titan's atmosphere. And it's an outstanding question that actually my group has been working on quite a bit recently to understand exactly how we end up with sand-sized particles from these much, much smaller particles in the atmosphere, but we do. and they get transported by winds on Titan's surface to form one of Titan's most characteristic surface features, these large sand seas. And then finally, one of the other places that we're interested in exploring on Titan is very, very rare. So one of the things that we first look for when we see the surface of a new world for the first time are impact craters. And the reason for that is that planetary bodies get whacked by asteroids and comets throughout solar system history. And so if you have an old surface, a surface that's about as old as the solar system itself, you have impact craters everywhere. You have so many impact craters that a new impact will just erase an old crater. That's the case on our moon, for example, which I think you're all familiar with. When we see a surface that doesn't have very many impact craters, that tells us that there's geologic processes resurfacing the surface of that world. And there are very, very few identified impact craters on Titan, on the order of about 10 that we know for sure are craters, on the order of about 50 more that we think are craters, but we haven't been able to definitively answer that question. And so that tells us immediately that there's a really lot of geologic processing happening on the surface. But we're interested in impact craters for a really important reason, and that reason is the following. Water cannot be liquid for long periods of time on Titan's surface. It is too cold. Titan does have a subsurface liquid water ocean like Europa and Enceladus. We always forget to tell people because we get so distracted by all of the other stuff I just told you about that we forget that there's a subsurface ocean, but there is one. But we really want to know what happens when liquid water interacts with those organics that are in the atmosphere that have never touched liquid water before. And the reason for that is that there are things called hydrolysis reactions. Water really likes to interact with organics. And when it does, it makes all kinds of new molecules that we're really interested in for life. And so we want to go places on Titan where liquid water has interacted with organics. And we don't have to go all the way to the subsurface ocean. When there is an impact on Titan, the rock that the impactor impacts into is water ice. Remember, that's what the surface is made out of. It melts from all of the energy of that incoming impact and forms a melt pool. The top of that melt pool flash freezes almost immediately because it is so cold on Titan. But that then insulates the pool of water below, allowing that pool to stay liquid on the order of tens of thousands of years, depending on how big the impactor is. That's a pretty long time in terms of chemical reactions. And so one of the things we really want to know is what kinds of chemical reactions happen in those types of melt pools. And spoiler alert, that particular crater is actually one of our targets for Dragonfly. So our current plan is to land just a little bit south of Selk Crater in an interdune region, which is nice and safe and flat for us to land in. And then we will make our way towards Selk Crater with an eye in particular on figuring out what has happened to all of those organics in Titan's atmosphere when they interacted with the water that was on the surface. Okay. So I'm just going to talk about some of these things in a little bit more detail and tell you why they're so cool. So just a little bit more about Titan's atmosphere. I already showed you this really cool picture of its haze. I'm just showing you it again so that I have an excuse to make it a little bit bigger. I mentioned that this comes from chemistry, and I promise this is the most complicated chemistry we'll have in here. The chemistry in the atmosphere is driven mostly by ultraviolet photons from the sun, so that light that we worry about when we're thinking about skin cancer, because it's so energetic, drives the chemistry in Titan's atmosphere. Methane is irreversibly destroyed in Titan's atmosphere, and so when it interacts with those photons and gets broken up, it isn't able to reform. So this is actually an outstanding question in the study of Titan's atmosphere, is why there is still methane in Titan's atmosphere, because the current abundance would be destroyed on the order of a few tens of millions of years at the rate that it's being destroyed now. And I even wrote a chemical reaction on the bottom for all of you, which is the methane interacting with light makes that ethane that I told you about before. Ethane condenses onto the surface to make those beautiful lakes and seas. It is a one-way trip. It won't evaporate with the amount of sunlight that reaches Titan's surface. And so once it's there, it's stuck. The other main molecule that is made from this chemistry is hydrogen. Because Titan is so small and its gravity is so low, hydrogen will not remain bound to Titan, and so it escapes. And so this is the reason why this is a one-way trip for methane, because one of the products condenses onto the surface and the other product escapes. The actual chemical processes look more similar to this. That's all I'm going to say about any of that. But to suffice it to say that the study of Titan's atmospheric chemistry is very complicated, and many folks, including myself, have spent the last, let's see now, 40 years trying to sort all of this out. We still have a bunch of outstanding questions. The main products of that chemistry, I've mentioned some of them already before: hydrogen, ethane. There's also things like acetylene and propane, hydrogen cyanide, CO2 and CO are actually made from the chemistry as well. So these are the main products that are coming from those complicated charts that I just showed you a second ago. One of the other really exciting discoveries that was made by Cassini, and I just put a pretty picture of Titan and Saturn behind this to distract you from the fact that I'm showing you this complicated graph. But the thing I want you to see from this complicated graph is that Cassini discovered that there are oxygen ions flowing into the top of Titan's atmosphere. And this was really surprising. This was something that was not ever predicted. And for the reasons that I mentioned before, to do with our interest in molecules that life cares about, we're really excited when we see that there's oxygen chemistry going on in Titan's atmosphere. This oxygen turns out to be coming from the teeny tiny moon Enceladus that actually has giant plumes of water shooting out of its south pole. Some of those water molecules get ionized and they hitch a ride on Saturn's magnetic field lines out to Titan, where they're deposited in Titan's atmosphere and can participate in all of the really exciting chemistry that's happening there. We know that it is primarily water in the plumes of Enceladus because after saying pretty please to the engineers about 1 million times, the scientists on Cassini were able to finally convince them to actually fly through the plumes, take the spacecraft through the plumes and directly sample them using something called a mass spectrometer. And we're able to see that the main molecule that the plumes are made out of is water. You can see there's a bunch of other stuff labeled on here, including some organic molecules. That would be a completely different talk about why Enceladus is so interesting. But for Titan, we're mostly interested in the fact that there is an oxygen source into the top of Titan's atmosphere to make that chemistry even more interesting than we thought it was before we made this discovery of the plumes of Enceladus. Oh, hold on. And just to say, the one other thing is that that oxygen source is actually the source of carbon monoxide through photochemistry, which you're seeing in this infrared spectrum. And carbon monoxide, as I mentioned before, is the 4th most abundant molecule in Titan's atmosphere. So actually, the plumes of Enceladus are responsible for the presence of the 4th most abundant molecule in Titan's atmosphere. I just think that's a really cool story and something really unique about solar system exploration, that we're eventually able to detect these connections between these different worlds and help us really understand the system, which is something that will be very challenging for a long time to do with things like extrasolar planets. And this is just saying that Enceladus has an ocean, which is pretty exciting. And now just showing Enceladus pictures, just because if you haven't seen this picture before, you should. It looks kind of like a rocket, or a lot of planetary people like to put a little cape on Enceladus. It looks like a superhero. So one of the other things that was pretty cool, and it's another graph, I'm sorry, that Cassini discovered about Titan comes from the same instrument that actually found those oxygen ions flowing into the top of Titan's atmosphere, which was the plasma spectrometer. So prior to the arrival of Cassini, the heaviest molecule that had been detected in Titan's atmosphere was benzene, which is C6H6. It has a mass of 78. And so our ideas were basically that we might have molecules up to a mass of like 100, which is like 6 carbon atoms, 7 carbon atoms, which is really complex chemistry in an atmosphere. We don't see chemistry more complicated than that anywhere in the solar system except for Earth. And the reason the chemistry in Earth's atmosphere is so complicated is because of life. So we thought that, you know, that would be what we were looking for. And that's actually what the mass spectrometer, which was designed to study Titan's atmosphere, the cutoff was 100. Luckily, the plasma spectrometer didn't have a mass cutoff, because instead of looking like that, which is what we thought it would look like, these data look like this instead. And so the bottom of this graph is effectively mass, so how much the molecule weighs. The side is just the number, the total amount of stuff. But what you can see here is that Cassini detected molecules that have a mass of up to 10,000. So remember, benzene was 78. I drew it here so that you can see. So C6H6 mass of 78, the most complicated thing we had detected in Titan's atmosphere before Cassini. And then this is what This is a fake thing that I drew in ChemDraw just to give you a sense of scale. It's not a real molecule, but that's something that has a mass of 10,000. So instead of 6 heavy atoms, 6 carbon atoms, we're talking about molecules that have 700 or 800 heavy atoms in them. And so we really seriously underestimated the chemical complexity of Titan's atmosphere. And this is one of the reasons why we're so excited to go back and try to understand it further, what that means for the origin of life on Earth, what that means for the possibility of life on Titan, and a lot of these big picture questions that we have. Just going to mention quickly what I actually do. So we do laboratory simulations of planetary atmospheres. And so we take simple, abundant atmospheric gases, we expose them to an energy source analogous to the way in which the sun is interacting with the gases in Titan's atmosphere. That initiates this chemistry that I've been talking about this whole time, and often makes these complex organic solids like these smog particles that we see, and then we can study them in the lab. When we do this, we see that we can make all kinds of molecules that are interesting for life on Earth. So here you're seeing the familiar ATCG of DNA and RNA. We also see the 2 smallest biological amino acids, glycine and alanine. And so these building blocks of proteins and DNA and RNA, we can form in these experiments in my lab when we simulate the chemistry that's happening in Titan's atmosphere. And so we have every reason to believe that these types of molecules are also present on Titan, were also present being produced by chemistry in the atmosphere of the early Earth. And so again, this is one of the reasons why we find Titan so exciting. I'm going to skip a bunch of slides in the interest of time so that we can have more questions, but we can always come back. These are mostly just a bunch of pretty pictures because Titan's really pretty. Yeah, I'm going to skip all these actually. Sorry. Oh, I'm not skipping this one though. So this is actually my favorite picture from Cassini, even though it's kind of blurry. And also this picture was not from the camera. So this picture comes from an instrument that was called the Visible and Infrared Mapping Spectrometer, or VIMS, which is why it doesn't really look like a picture, because it wasn't really meant to take pictures in that sense. But what you are seeing in this image is the first sun glint from another world. And so this is sunlight reflecting off of a lake on Titan's North Pole, one of these methane and ethane lakes. It turns out that they were able to kind of reverse engineer based on where we knew the spacecraft was at the time and doing some ray tracing with the way that light would bounce. They figured out which lake this light actually bounced off of. And it turned out that that lake hadn't yet been named. Lakes on Titan have to be named after lakes on Earth. And so it was suggested that this particular lake be named Jingpo Locus, which means mirror lake, because of this first sun glint. And I just think this is so cool. It really hits home this idea that there is another world in our own solar system that currently has standing bodies of liquid on its surface, that if you wanted to go sailing in, you certainly could, although it would be very, very expensive to get there at this point. And that's just to show the imaging data where that lake is. I'm going to skip these two. Okay, this will give us a few seconds to talk about Dragonfly. So one of the reasons why we're so interested in Titan is it presents us this really unique opportunity. So I mentioned that we have this subsurface liquid water ocean. That means that there is the possibility that there is water-based life on Titan. So life as we know it, it uses water as its solvent, it uses carbon to do all of its information containing and transport and all the things that carbon-based molecules do for us. So we have the possibility to search for life as we know it. And that lets us answer the question of whether or not life is ubiquitous. If life is ubiquitous, then anywhere it has water, organics, energy, and some time, there should be life there. We don't know yet if life is ubiquitous. But on the surface, we have those lakes and seas that I just talked about that are made of ethane and methane. And that lets us test a different question. And that question is life diverse? If life is diverse, it should be able to take advantage of different solvents. So it shouldn't need water as a solvent. It should be able to use methane or ethane. It should be able to build a different chemistry and figure out how to exist. And so Titan is the only place in the solar system at this present time where we have a liquid on the surface that is not water, where we can test this question of whether or not life is diverse. And finally, even if it turns out that there is not life on Titan now, there was never life on Titan, there never will be life on Titan, we're still able to go through all of these chemical processes that I was talking about that we think lead to the origin of life, and think about how that chemistry occurred, what that means for what was going on the early Earth, and even think about why, if Titan does seem to have all of the ingredients for life, there isn't life. And so the great thing about Titan is, regardless of the answer, whether or not there is life as we know it, life as we don't know it, or no life at all, exploring Titan is really going to let us understand a lot of questions that we have about life in the universe and the origin of life here on Earth. And so to do that is Dragonfly. So the short version explaining Dragonfly is that it's a mission to explore Titan's prebiotic chemistry and habitability using a mobile platform. That mobile platform is a dual quadcopter, or we often call it a Rotocraft lander. So it's a relocatable lander. It can land and then do some science and then take off and fly somewhere else and do some science, taking advantage of the fact that Titan has low gravity and a thick atmosphere. And so this is just a little further summary. So mobility is really great to be able to access all of those diverse terrains that I just barely had time to touch on today. And because the gravity is 1/7 of Earth and the atmosphere is 4 times denser, it is much, much easier to fly on Titan than it is on Earth. In fact, if you had wings that you built from whatever you could find at Home Depot, and you were standing on the surface of Titan and you started flapping those wings, you would be able to fly yourself under your own human power. It is that easy to fly on Titan, and Dragonfly is taking advantage of that. And then we'll do surface measurements, in particular, really doing detailed composition measurements to understand what that material is made out of. Remember, the complex organics that are made in the atmosphere end up on the surface, where it's very easy to access them. We can drill to be able to get that sample and then ingest it into instruments to measure the composition. We'll also be doing things like meteorological measurements. We have a seismometer to look for seismic activity. We'll be taking tons and tons of pictures to help us understand geology at all different scales. All of those things are very important for understanding Titan's habitability. And so we're really, really excited about Dragonfly. And I have just a little, which will hopefully work, but sometimes doesn't always work, animation of how Dragonfly will proceed. So when we arrive at Titan, we're on parachute. This will definitely be the most terrifying moment of my entire life because we fly off of parachute rather than gently landing. So at least by the time we get to the ground, we already know whether or not we can fly. We'll fly to our original landing site, which, as I mentioned, is a little bit southeast of Selk Crater. We'll land, we'll be able to do all of our different types of sampling. We have 2 drills, which you can kind of see in this animation. There's one on each skid. We'll take samples, we'll analyze them, we'll send that data back to Earth. You can see that high gain antenna that just hinged up and went to talk to Earth. We talk directly to Earth. We have no orbiter. We're not relaying data back like the Mars rovers do. We have to talk directly to Earth. And then once the scientists all agree that it's time to move on, we'll pack up things and we'll fly to our next destination, where we'll be able to do all the same types of measurements again, over and over again, for probably about 2.5 years is our nominal mission. We can last for longer than that, assuming everything goes well. NASA continues to want to fund us. And so we'll be able to fly pretty far and explore a lot of the really diverse terrains that we see on Titan, and hopefully answer some of those really exciting questions that we have about life. And with that, I would love to take questions. Thank you so much for your attention. I really appreciate it.
Thank you, Dr. Horst. You could use virtual applause for our speaker and the reactions. Thank you so much for that wonderful talk. I'm so excited to ask a lot of questions about Dragonfly. If you have any questions for the speaker about their research about Titan, please ask them to me in the chat. I'll be moderating the question A for the next little bit, and then we will have a remote telescope viewing session. So you answered one of our questions, which is that we received, which what is the surface gravity on Titan? And you said that was what?
It's about 1/7 of Earth.
Okay, sounds like a place I might enjoy work, not for the frigid temperatures. And we had another question. Carbon monoxide is an unstable molecule. Is it more abundant on Titan because of the low temperature?
Carbon monoxide is actually quite stable. It has a triple bond, which is one of the hardest bonds to break. And I think the main reason that we don't have a ton of it in Earth's atmosphere is just because we have a really lot of reactive oxygen chemistry in Earth's atmosphere. And so one of the things that carbon monoxide can get converted to is carbon dioxide, which also happens in Titan's atmosphere, actually, just not at a super high rate. And so one of the reasons we have as much carbon monoxide as we do in Titan's atmosphere is actually because it's a quite stable molecule because of that triple bond.
Great. Thank you for the chemistry lesson. Someone asked, they wonder if you have worked at Kitt Peak.
I never had the benefit of actually working there. I got to visit a couple of times and see the amazing telescopes that are there. And I made the regrettable decision once in a while to ride my bike up Kitt Peak when I was living in Tucson. But I've never actually gotten to observe in any of those telescopes, which is kind of a bummer, honestly.
Yeah, on your website, are you do you do triathlons or marathons? Is that the?
I used to do triathlons. Now I mostly just run and bike.
That's awesome. Yeah, I'm an avid cyclist these days myself, but I need a little help, so I have a pedal assist.
Nice.
We just moved. I used to live a half mile from George Mason, and now I live about 3 miles. So I'm gonna finally have a real commute on my bike. Okay, so we have another question. I guess one of our guests here tonight was just in Tucson last week, and that was the one who asked about Kitt Peak. It's another question about Dragonfly. What are the average wind speeds on Titan? And is there a concern of Dragonfly being carried away uncontrolled?
Yeah, that's a really great question. So the long story, which I'm just going to tell because I'm here, is that it's actually really challenging to measure wind speeds on other planets. So on Earth, we just set out instrumentation like anemometers. We can directly measure the wind speed, super easy. Anybody can basically do it at home at this point. Unless we send a fleet of anemometers to other planets, it's actually really hard to measure the wind speeds. The main way that we do it is through what we call cloud tracking. We take a really lot of pictures and measure the clouds moving. And I have personally done this for Saturn. I can tell you it's one of the most boring things a human could possibly do, but nonetheless, it's really important. One of the challenges with Titan is that although we do have clouds, they tend to be relatively infrequent, and they're very seasonal. And so there are seasons on Titan where we have no wind speed information at a given location because there haven't been any clouds there. We have one direct measurement of the wind speeds that was done by the Huygens probe. And so we looked at the Doppler shift of the signal from the Huygens probe moving as it was blown around by the winds. So that means a couple of things. One, we don't have a lot of wind measurements for Titan. But the wind measurements that we do have tell us that most of the time the wind speeds near the surface are very, very low. And the other thing that helps us, which I didn't mention when I was talking about Dragonfly, is that as currently planned, we land on Titan at almost the exact same time in a Titan year as the Huygens probe descended through Titan's atmosphere. And we're going to land at a relatively similar latitude. So we're taking advantage of the fact that we do have that one measurement of the wind profile. And we have everything else we've learned from the wind measurements that we do have, and a lot of atmospheric modeling. And all of those things tell us that the wind speeds near the surface are really, really low for most of Titan's year. There is a period of time near the equator where we think the wind speeds get very high. I mentioned that there are big storms that occasionally happen near the Huygens landing site where we see those washes. We probably wouldn't want to be there then. So we are actively avoiding that part of Titan's year so that we have very boring conditions. One other thing to mention when folks often are like worrying, are we going to flip over or something? Dragonfly is not the toy drone that everyone has at home.
Yeah, I was gonna ask you, have you ever flown a toy drone? It always flips over on me. But
yeah. So Dragonfly is about the size of a Mini Cooper.
Wow, it's
And
huge.
so flipping it over is will be non-trivial. And so it would take quite a gust of wind to actually do something like that. But we also have to be careful. And so it's one of the reasons why we have a meteorology package on the spacecraft. So we can monitor things like the wind speed, the methane relative humidity, and the temperature before we decide to fly. So we'll have our like pre-flight weather check. But if something changes during flight, Dragonfly will also be able to be like, oh no, this is really bad. I'm landing now, sorry. And that's one other thing to mention that people often ask about. The one-way light time to Saturn is about an hour. So Dragonfly will be flying on its own. It will have a predetermined, flight path and where we want it to land. But once it takes off, its onboard computer is in charge of all of the decision making, and we will just be sitting on Earth waiting to hear how each flight went. And so it has to have a lot of resiliency in that decision-making process and the ability to say, everything that is happening right now tells me I shouldn't be flying. So I'm going to stop flying now and I'm going to go land. And then you're going to tell me what to do because something bad happened. We will know more about the winds on Titan after Dragonfly is the short answer to your question.
Yeah, that's amazing. I would not want to be the person that has to make that programming decisions on that flight software. Wow.
Me neither.
I have to say that's been the biggest shock to me so far is how big this thing is. I didn't really have a sense of scale from the pictures and videos I've seen. So it's about the size of the Mars rovers.
Yeah, it's I think intermediate to the Mars exploration rovers and Curiosity. So it's not as big as Curiosity, but I think it's bigger than Spirit and Opportunity. And of course, this is still we're not cutting metal yet. And so, a lot of these things are still a little bit TBD. I know that our folks who, designed the kind of aerodynamic profile of Dragonfly did it as fast as they could during the proposal phase and would like to make it more aerodynamic. And so we don't have, our final ideas yet about exactly how big the spacecraft will be, exactly how heavy.
I'm gonna take the host privilege and ask a question. So I was thinking something like the size of a shoebox and not the, like a drone and not the size of a desk or something like that. And so this must be pretty expensive then. What's the cost of the mission?
So Dragonfly is a New Frontiers mission, which is a medium cost mission for NASA planetary science. So the other New Frontiers missions, which hopefully folks have heard of, are New Horizons was a New Frontiers mission to Pluto. Juno, which is currently in orbit around Jupiter, was New Frontiers 2. New Frontiers 3 is OSIRIS-REx that just retrieved samples from the asteroid Bennu and is going to bring them back to Earth. And we're the 4th one. Those missions have a cost cap of $1 billion. And so that's kind of the scale that we're looking at in terms of this mission. Actually, the cost cap is lower than that. It's rocket cost is complicated the way NASA does it, but we're on the order of $1 billion.
So in astrophysics, we call that a probe class mission rather than New Horizons. So or New Frontiers. That's actually not that bad because I think the latest Mars rover that just launched was like over $1 billion.
$2.5 billion, yeah.
Yeah. So maybe you could build 2 of these for us.
I mean, if NASA would let us, I'm sure we would happily build a whole fleet.
That would be awesome.
I think they're going to have us stick to one for now.
Yeah, I guess we'll see. So another question we have, is it known why Titan has an atmosphere when Ganymede, which is a touch bigger, does not?
That's I love when people are like really sharp. We don't know. We have some ideas, which are not, I think, particularly robust. One of the most obvious answers is that Ganymede is closer to the sun. So the two things we really care about for retaining a planetary atmosphere are gravity, which is related to size. So in that sense, Titan and Ganymede are effectively the same. And temperature, because the velocity that the gases have, because of their temperature, is what helps them overcome the gravity and escape. So atmospheres stay on big cold places. So if you're little, you want to be colder to hold on to an atmosphere. Because Ganymede is closer to the sun, it's inherently warmer. And so it's possible that in and of itself is the main reason why Titan has an atmosphere and Ganymede doesn't. But it's really an outstanding question. It turns out that we don't know a lot about how terrestrial planets get their atmospheres. It used to really bother me that we didn't know why Titan had a nitrogen atmosphere. And then I found out that we don't know why Earth has a nitrogen atmosphere. And that made me feel a lot better. So it's definitely something we think about a lot. We have these two places that are very similar in terms of size, both orbiting giant planets. One of them has a massive atmosphere and one of them has no atmosphere at all. And it's certainly a question that I wish I could tell you the answer to.
Yeah, that is a pretty insightful question. Thank you to the person who asked that. All right, so next question we have, and you answered this partially, it's a two-part question. How much is the information travel time with Dragonfly, and how long will it take for Dragonfly to send information to Earth once it's at its destination?
Yeah, so like I said, the one-way light time is about an hour.
Did I break up a little?
You did, but I heard the question. Can you hear me? Can anyone else hear me?
I can hear you. I think.
Okay.
I can hear you.
Okay.
I think it's Peter that's
Yeah, I
breaking
can
up.
hear you.
Okay. I can repeat the question because I think I understood it. So the first part of the question was basically like, how long does it take for information to travel back and forth? So the one-way light time is about an hour. In terms of sending all the data back, I don't actually know the answer to that question. I think this is one of those things that's going to depend a lot on kind of the final details of the way that the mission ends up getting designed once we're able to start cutting hardware. So I'm wondering if the person is thinking about New Horizons, which took so many painfully slow months to send all of the data back from the encounter. We're not going to take that long for each flight. And the reason for that is that we don't want to just be sitting on the surface forever transmitting the data back to Earth. And we're not going to be transmitting the data back when we fly because we need all of our power to be able to fly when we're flying. And so there's a balance there of taking enough data that we get our science done, but not taking so much data that we're just sitting on Titan telling Earth painfully slowly how, what we were able to find. And so that's definitely a balance that we have to think about in terms of power management, data volume. Also, because we have to talk directly to Earth, we have periods of time when we cannot send the data back because we can't see Earth. And so that's another constraint that we have in terms of all of those different things. So it's definitely going to have to be a coordinated dance to figure out how that will be. But I promise you that it will not take I don't even know, it took like 1.5 years to send all the New Horizons data back or something like that. But we're not going to do that to everybody. That was painful, although totally worth it, but also painful.
Okay, so at this time it's about 9 o'clock, and this is a little after 9, and this is when we normally transition to our telescope tour. If you're willing to stick around, Dr. Horst will take some additional questions during the lulls in our telescope tour if you are willing to stick around. But let's give another virtual round of applause for our speaker tonight. And that was just amazing. I have a ton more questions to ask. So I'll go ahead and turn it over to our students, and they'll take over, and then I'll ask a couple of questions if you can stay on.
Yeah, that's fine.
Okay, wonderful. Yeah, great. So I hope you all enjoyed Dr. Horst's talk. So right now we'll transition to the virtual tour part of the evening. So let me just share my screen here. Okay, let me minimize that. All right. So just to give you all some context of what you're looking at, so we are connected to a computer. We're looking at the desktop of that computer. And that computer is located in this building off to the left of the dome. So this computer lets us control the telescope pretty much fully. So one of the things that makes it possible or safer to remote observe, like I'm doing now, is we have a series of webcams mounted on the roof of the building. And if I pull those up, we can see a view, 3 different views. So going through these one at a time, in the top right, we have the inside of the control room. So we're currently connected to this computer right here off in the middle left. We have a secondary computer in the bottom left that's a clone of the primary computer, and we do all of our software testing on there and whatnot. But observers, when they are observing in person, would spend the entire night, or most of the night, in this little small room saying that they're going to be productive, but they end up just watching YouTube and movies. So that's the control room. In the bottom right, we have a no signal camera. That camera is inside a box, so we don't really expect anything there. Then in the bottom left, we have an outside view of the roof. We have the dome, so the telescope is inside the dome. And you can also see that it is quite cloudy. So if we, then in the top left, we have the telescope itself, and I'll talk about that in just a minute. But one thing I want to show is a new camera addition that was installed fairly recently. It's a, technically it's an all sky camera, but as it's currently mounted, it's really a half sky camera. So if we just move this over here and I pull this guy up. So that half sky camera is mounted a little off to the side, to the left side of the dome. And that was interesting team viewer notification. But anyways, that full sky camera is mounted a little on the left side of this dome. So that's what you're seeing here. You're just seeing a part of the dome and not the rest of the sky. But anyways, the point is you can still see half of the sky, and you can see it's very overcast. I took this image about 15 minutes ago. So unfortunately, this means we're not going to be able to open up the telescope. So if I just take another image right quick, we'll be able to hopefully see the clouds shift a little bit. So for those who like watching clouds, this might be interesting. But
Hey, William, while we're waiting to watch clouds, our speaker does have to leave soon. So I'd like to ask one more question of Dr. Horst before she has to leave.
Sure.
And so Dr. Horst, you know, one of the things that's always fascinated me is what it's like to work on a NASA mission that flies to another world that takes so long and such a large piece of your life. So can you tell us when Dragonfly will launch, when it will get there, and kind of just personally what that experience is like, or what you think it may be like as you're moving forward to it?
Yeah, so we've been working on Dragonfly for, I guess, 3 years now, 4 years, somewhere in that neighborhood, in terms of the like proposal process and all of that. Our original launch date was 2026. Because of the impact of COVID on NASA's budget, especially the missions that are trying desperately to launch this year, or that managed against all odds to actually launch this year, NASA had to spend more money to make those things happen because of COVID. And so since we're in the very early stages of actually building the spacecraft, they asked us if we could delay our launch to help them reallocate some money. So we're not going to launch until 2027 instead. We haven't actually finished replanning the way that we get to Titan in terms of gravity assists from Venus and Earth and all of those things. And so we don't know yet when we're going to get there. Our original landing date was 2034. We will probably get to Titan with a 2027 launch date of more like 2035 or 2036. So yeah, that's a long time. By the time the mission is over, if we go into extended mission, I will have probably worked on Dragonfly for 20 to 25 years, which is a huge fraction of a person's career. We're obviously in the early stages of that, but I can tell you from having watched the Cassini mission team, which was kind of a similar scale in terms of when the instruments were selected until when the mission ended, that it becomes a big part of your life. Your collaborators become like your family. Folks watch each other's kids grow up. They go to weddings. They do all of those things. And my favorite thing about Dragonfly, besides Titan, is how amazing the science team is, how much fun we have together. And so I'm just thrilled to spend the next 20 years working with this amazing group of people, because they really truly are amazing.
That is wonderful. Thank you for sharing that with us. So thank you, Dr. Horst, for joining us. We will be posting this video to YouTube, and we'll send you the link later.
Great.
And we look forward to having you back in the future in person.
Yeah,
maybe
sure.
Every 10 years or so, 5 to 10 years, to hear how the mission's going. Okay,
yeah,
fantastic.
Sure.
Good
All
luck with Dragonfly. That was
Thank
so
you
exciting.
so much. Take care.
Have a good night. Okay, William, back to you.
Okay, thank you. Right. So as I was saying, it's pretty clouded out. You can see that in this half sky camera, all of those clouds. So we're not going to be able to actually take any images of the sky tonight, as Peter said at the beginning. But we do have a set of images that we can show you that we've taken beforehand when the weather was clear. So before we do that, though, I just want to talk a little bit about the telescope. We have some students, I believe, in the call tonight, and they need to know a little bit about the telescope, I think. So in the top left, we have our big boy, the GMU telescope. So this is a 0.8 diameter telescope. So the aperture is about 0.8 meters, 0.8 meter diameter. So the way light works in this telescope is it'll come in through the big opening here, and it will bounce off the primary mirror. That's that shiny reflective surface in the back of the tube. And then it's going to bounce up to this secondary mirror here, which is about 12 inches in diameter. And then that light will pass through a hole in the primary mirror. You can kind of see you have this black cone, or cylinder rather, in the middle of the primary mirror. And that's just a hole where the light will pass through. And it will bounce off a diagonal mirror where that light is then reflected into one of the instruments we have on the back of the telescope. So this is a reflector telescope as opposed to a refractor, meaning that it uses mirrors instead of lenses. So as I just said, the light is going to be bouncing off the mirrors instead of passing through the glass. So it turns out that reflector telescopes are easier to make than refractor telescopes when they get very, very large. And the reason for that is fairly straightforward. You can support the reflector, the mirror, over the entire back of the mirror. Whereas with the refractor, you can only support it around the edges of the mirror. So glass can be very heavy when it gets very large. So it becomes a lot more difficult and more expensive to support it. So that's why some of the largest telescopes in the world are reflector telescopes. So in terms of size, this is a fairly large telescope. It's one of the largest publicly accessible telescopes on the eastern seaboard. And as I said, it's about 0.8 meters, 32 inches in diameter. But some of the largest telescopes in the world are about 10 meters in diameter, so about 10 times the size of this telescope. And perhaps that would carry a little bit more weight if you could be there in person and actually see the size of this thing and then imagine something 10 times the size of it. That'd be pretty impressive. But anyways, the telescope itself, right quick, is about $300,000. The dome itself is about $80,000, and then about $150,000 worth of upgrades were poured into it between 2017 and 2019-ish, something like that. So that's the telescope in a nutshell. I can answer any additional questions in the chat later, but for now, let me go ahead and turn it over to Owen, who can pull up a picture of Saturn. Since Dr. Horst talked about Titan and Saturn a little bit, we should probably show one of the images of Saturn. So if Owen, you could pull that up and tell us about Saturn.
All right. Hello. Sorry. Having trouble unmuting myself. Where is it? So, here is Saturn through our telescope. You will notice that it is very, very small. And this is because we have an angular resolution of about 26 arc minutes. And so the planets end up being really small, but our wide field of view is good for research observing, which we do quite a bit of. So Saturn, as we discussed earlier in the tour and during the talk, has a bunch of moons, mainly Titan. Another interesting one is Enceladus. Let me see if I can get one of our nice stock images. And so Enceladus, I think it was mentioned earlier, has a subsurface ocean, and this is due to the tidal heating of the system. So Jupiter, or not Jupiter, Saturn, Titan, all the other moons in the solar system have some sort of some level of gravitational effect on Enceladus, so they pull on it, and eventually enough heat is added to the system to where there's liquid water under the surface. But there's actually also cryovolcanoes, which are basically geysers but with ice. And so these are what's interesting about these is that they make up what is known as the E ring. It's a super faint ring around Saturn, made up solely of the ice coming out of the cryovolcano on Enceladus. Let's see. So I think Enceladus is pretty cool. I even got a poster. A while back, NASA had these like posters that they made of like different destinations in the solar system, and so one of them was Enceladus. They did a few for Mars, but Saturn, here's all its moons. Not all of its moons, but a good chunk of moons. It's got about 67 moons. So it's a gas giant. What's interesting about Saturn is that it's so least dense. No, its density is such that it's less than water. So if you had a giant pool of water the size of the solar system, Saturn would float in it. And so its rings, like I sort of mentioned earlier from Enceladus, its rings are made of water, ice, rocks, dust, but it's super thin. So at points during its orbit, we look at Saturn, and it looks like there's no rings, just because the ring is so thin and we're looking at it plane on. Another interesting feature about Saturn is, I don't know if we have a picture of it, but it's got a funky hexagonal storm on the North Pole, which scientists do not know the cause of it, and that's really unfortunate that I cannot find a picture of it. But yeah. With that, I will turn it back over to Justin.
All right, thanks, Owen. Thanks for telling us about Saturn. So yes, Saturn does have a very interesting hexagonal storm at its north pole. I don't think we have a picture of that, but it's something we should take a photo of there, or we should get a photo of, rather. There are some nice photos floating around of that.
Oh, I should also mention that Jupiter and Saturn are going to be at conjunction on the 21st, which means that they will be super close together in the sky, only about 0.1 arc minutes apart. And so we should be able to get a pretty nice picture of that in our telescope. So I'm excited for that. It's happening on the solstice, the winter solstice.
Yeah, definitely. As we get to the winter solstice in a few weeks, please go outside. Hopefully it'll be a clear night. And this will be it'll be at the closest on the 21st, but you'll be able to see them fairly close in the sky throughout the rest of December as they get closer and closer. And it'll be a really beautiful sight to see with your own eyes in the night sky this winter. We have some questions that have been coming in the chat just to answer a few, and I'll ask them of William. What is the aperture of the telescope and the focal length of the eyepiece? And then maybe we could take the telescope for a spin and show the telescope moving around.
Sure. So as I said, the aperture of the telescope is 0.8 meters, or equivalently about 32 inches. We're not really using, when we show people images of the, or take images with the telescope, we aren't exactly using an eyepiece, we're using a CCD. So the CCD itself doesn't really have a focal length, so you can just put the focal ratio of the telescope itself, which is f divided by 7. So don't worry about the notation, that's just a notation. So you can just write f over 7 for the eyepiece focal length. So basically that just tells you that the telescope is kind of well suited enough for both a wide field viewing and kind of more detailed viewing. So was there any more to that question, or was that?
Yeah, you got it. Yeah,
Okay.
We could go ahead and take a telescope for a brief spin, and I hope you all have, for those of you that have joined multiple of our public nights, we've had some horrible weather here this semester in Northern Virginia area. That's 2020 for you, and we thank you for joining us. All of our public nights are available to watch on our YouTube channel, and we are going to be working on an exciting lineup of speakers and stars to look at for the spring semester. William, back to you.
All right, thank you. So I am just currently moving the telescope just so you can see it actually moving live. So you can see that we have the fork of the telescope coming into view now. So this telescope is mounted to this tuning fork-like object that'll move it around, and we can have a full range of views so we can see pretty much the whole sky. So once this finishes moving, or I can just do it now, rather, I can also go ahead and spin the dome around. So let me just connect you. Okay. And then if I go ahead and just hit home, we can see the background in the camera. The dome itself is going to start moving. And I personally miss hearing the sound of the dome. I think it makes a really cool sound. The way I like to describe it is a spaceship getting ready to jump into light speed. That's what it sounds like to me, and no one ever seems to agree with me on that. So you'll just have to come back in person and see if you think I'm crazy or not. But anyways, that is a little bit of movement in case you were interested in checking that out. So unfortunately, there's really not a whole lot I can do there. But anyways, we have one more object we want to show you tonight, and that is the Orion Nebula. And we will have Andrew tell us about the Orion Nebula.
Cool, thanks, Will. So I was having trouble connecting with TeamViewer again. The authorization of it. Could you just like pull up the image for me? Sorry about that.
Yeah. Sorry, I forgot to give you the updated connection.
You did give it to me. It's just that I think you need to authorize the entry or something.
Oh, I do. Okay.
Something like that, yeah.
All right. Well, here's a picture of Orion. Is this the one you want?
Sure. I'm not sure how many other images you have.
We have.
Oh, you have quite a few. Okay, just whichever one's the clearest, I guess.
Yeah. Okay, we can just do this one.
Okay. So there's the picture of the Orion Nebula. So the entire nebula, so the prominent stars actually within the constellation are 3 stars in a short row called the Orion's Belt. Where would that be on here? Oh, right there. So there's 1, 2, and 3 in a about 45-degree angle on the upper right. And those are the 3, that's called the Orion's Belt. And then under that, there's an area called the Sword of Orion, which is basically like a curved line of stars below the belt. Yeah, and most nebulas can't actually be seen, usually can't be seen with the naked eye, and you usually need to use equipment, or basically you need to use equipment to be able to see it in different spectrum of light that they usually emit. But for this one in particular, if you go to a more rural area, or just have a simple backyard telescope, you can see this. So that's a really cool thing about this nebula. It's about 1,300 light years from Earth, and it's about 30 to 40 light years in diameter. And it's actually actively forming approximately 1,000 stars. So it's a huge cloud of gas with a lot of condensing areas forming into new stars. Most of the stars actually in the Orion Nebula right now are actually only about 1 to 2 million years old, so they're pretty young. They're very young, hot stars. Especially, you all have probably heard of the name Betelgeuse and Rigel and Sirius. So Betelgeuse and Rigel are actually the brightest stars within this nebula. One of them is a red giant, and a red supergiant, I believe now. And then Rigel is a blue giant. So Betelgeuse actually a few months ago was thought to have. There was I think an image was taken, maybe it could have gone supernova or something, but then we realized it actually didn't, and it was just something obstructing its view, and it was actually a mistake. So we still have a little bit while, anywhere from tomorrow to a few centuries or so, until we'll see signs that it actually go supernova. But in stellar terms, that's actually a really short window. That's really nothing. Plenty of stars can live billions or even trillions of years, but these guys have only been around for about 1 to 2 million years, and will only live a few dozen to a few hundred million years. What's really interesting about this nebula is that there's still a lot of discoveries still being made about it. For example, in 2012, astronomers found very strong evidence that there's probably a black hole at the center of this nebula. And the reason why they found out is because a lot of these stars in the nebula are moving at very high speeds. They're either being flung around or they're orbiting, and it looks like the nebula is it seems like it's being pulled apart, and they don't really know why, because there's no obvious gravitational influence visible. But in between the trapezium, which is actually a young cluster of stars forming at the same time, there's a huge gravitational influence, and there's likely a black hole of about 200 times our sun's mass. So it's not super small, it's not too large, but it's nonetheless a black hole causing this strange activity. And I forgot to mention, there's a young open star cluster called creatively called the Orion Nebula Star Cluster, which is a cluster of stars forming at the same time towards the center. So that would be that huge hot gaseous area right around that area right there. But in general, the trapezium is best seen in the infrared spectrum. If you were to see this, I don't think this image is an infrared spectrum, but if it was, there would be really prominent 4 dots. It looks more like a slanted rectangle, but it's called a trapezium. That would be really evident within the center. That's all I really have for this nebula. Is there any questions about it anybody has? Good.
Thank
Okay,
you,
good.
Andrew.
Thank you.
Thank you, Andrew. One last thing I'd like to add. The Orion Nebula is one of the most popular winter astrophotography targets. It's very large and fairly easy to find. So it's if you have the right equipment, it's great to try and take an image of it. So hopefully back in when January rolls around, we'll have some clear skies and we can take an image of this beautiful nebula. But before then, you might also want to try and look at it yourself if you have just a pair of binoculars or your own telescope. It's fairly easy to find and you can actually kind of see it with your naked eye. You'll not be able to see, you know, this level of detail, but your eye will be able to tell that there's a little bit of a smudge in the sky, particularly if you're in more of a darker area and not a cityscape. But anyways, I think this is going to conclude our virtual tour. So thank you all for joining us this evening. I hope you enjoyed it. And hopefully in January, we'll have clearer skies. And next semester, we'll have clearer skies. So yeah, thank you all. We'll post the schedule for next semester as soon as we can on our website. Thank you.
Yeah, stay tuned on our website. We hope to see you in 2021 on the other side of this 2020 year of a dumpster fire. So have a good night, everyone. I'd also like to thank William, Owen, Andrew for hosting tonight and giving us the tour of the night sky.